Good morning, everyone. My name is Anish Meduri, and I'm from Mechanical Theory. So today's topic for FEA AAT2 is gear tooth sliding velocity in a wind turbine gearbox. Introduction: Wind turbine gearboxes convert low speed rotor motion. Yeah, one second. Low speed rotor motion, 20 to 30 RPM into high-speed shaft motion, that is 1500 to 1800 rpm for electricity generation. These gearboxes face high torque and varying loads. One critical factor in their efficiency is gear tooth sliding velocity, which is nothing but it determines friction, wear, and heat generation. Also, understanding this helps improve gearbox life and reliability. So, yeah, this is the introduction. You can go through it and objective. To analyze and derive gear tooth analyze and derive gear tooth sliding velocity in a wind turbine gearbox is what the objective is. What is the objective? To analyze and derive gear tooth sliding velocity in a wind turbine gearbox. To understand how geometry and motion affect sliding velocity is another. To examine its impact on performance and wear is another. It's nothing but to examine the impact when you perform it. We need to examine the impact on the performance and the wear. Another one is to explore methods to reduce sliding velocity through design and lubrication is what another is. It's nothing but to explore methods to reduce sliding velocity through design and lubrication. So yeah, these are the objectives. Now we'll go to gearbox functions in wind turbines. So yeah, wind turbines require a gearbox to match rotor and generator speed, right? This is what gearbox and function in wind turbines, right? What do we need? We need wind turbines which requires a gearbox to match rotor and generator speed. Okay. Types of gearboxes. Planetary gearbox. Planetary gear stage. Handles high torque from rotor. Parallel shaft stage. Increases speed for generator input. These are two types of gearboxes. Planetary gear stage handles high torque from rotor. Parallel shaft stage increases high speed of generator. Gears are mostly helical or planetary for smooth transmission. Continuous meshing of gear teeth leads to sliding and rolling motion. Gear tooth kinematics. Key definitions. Rolling velocity, VT. It's nothing but tangential velocity common to both gears at pitch point. And another key definition is sliding velocity, VS. The difference between tangential velocities of contacting point of two teeth. That is nothing but Vs equals to Vt1 minus Vt2. At pitch point, Vs equals to 0. When you pitch, both of them, at that point, Vs equals to 0. At the start and end contact, Vs is maximum. Okay. Diagram. Involute gear tooth contact path showing start A, pitch point P, and end B of contact. This is what the diagram is, okay? Derivation of sliding velocity. For two meshing gears, Vs1 equals to omega 1 Ra minus Rb. That is, and Vs2 equals to omega 2 into Rb minus Rp. Hence, due to this, Vs equals to Vs1 plus Vs2 equals to Rb1 omega 1 plus Rb2 omega 2 sine phi. Where Rb1, Rb2 is base circle radii. Omega 1, omega 2 is angular velocities. Phi is pressure angle. Observation: Vs is angular speed. Vs with gear ratio and pressure angle. Graph sliding velocity versus contact path 0 at pitch point. is what this is about, right? So yeah, we'll just go to the next slide. Given pinion speed. This is a numerical example. We'll go through this. There's a pinion speed which goes 1800 rpm, and R1 equals to 50 mm, R2 equals to 150 mm, phi equals to 20 degrees. Base circle radius RB equals to R cos phi, right? So we need to find RVS. Vs equals to RB omega 1 plus omega 2 sin phi. Now, omega 1 is 2 pi n1 by 60, right? So now put this in the equation. We'll get Vs equals to RB 2 pi n1 by 60 equals to sine 20. That is Vs equals to 2.61 meter per second. Result: sliding velocity equals to 2.64 meter per second. Moderate but significant for frictional heating. Effects of sliding velocity on gear performances. Frictional losses, power loss proportional to FVS, heat generation, increases tooth surface temperature, and wear and pitting, which means nothing but accelerated material fatigue due to tangential slip. Wear and pitting means accelerated material fatigue due to tangential slip. Lubrication, film breakdown. Thin film failure leads to scuffing. Okay. Vibration and noise. Uneven wear alters meshing characteristics. So that is effects. We'll go to the next slide. Factors affecting sliding velocity. Gear ratio, higher ratio. Gear ratio is I. Okay, that is higher ratios to higher sliding velocity is gear ratio. Pressure angle is increases sliding. Tooth geometry, that is modified involute or in asymmetric teeth reduce sliding. And then we have helix angle, which is B. Helical gear have combined rolling and sliding. Surface roughness and hardness. Rough surfaces increase frictional losses. That's right. And then we have lubrication conditions. What are the lubrication conditions? Temperature and oil film thickness is critical here. So those are the factors affecting sliding velocity. Reduction techniques. Profile modification. Optimize involute profile to balance sliding and rolling. Helical gearing distributes contact load, reduces instantaneous sliding. Advanced lubricants, synthetic oils or grease with EP additives. Surface coating, TLC, diamond-like carbon. Nitriding or carburizing. And then we have precision alignment. What is precision alignment, you may ask? Precision alignment is nothing but reduces misalignment induced local slip. Real-time monitoring sensors track to torque, speed, and temperature to predict wear. These are the reduction techniques: profile modification, helical gearing, advanced lubricants, surface coating, precision alignment, real-time monitoring. Simulation analysis. Finite element analysis FEA or multi-body dynamic simulation MBD helps visualize stress or velocity fields. Software used are ANSYS the most the main software. Romax is soft or MATLAB SimSpace. And the simulation outputs are tooth contact stress distribution, sliding velocity contour, thermal loading prediction, validated using experimental gearbox data. So these are the finite element method, simulations and analysis. Conclusion. Gear tooth sliding velocity is a key factor in gearbox performance. Okay. High sliding velocity, that is where heat and efficiency loss takes place, can minimized by optimized design, advanced materials, and effective lubrication. Improved understanding ensures longer life and higher reliability in turbine gearboxes. With this, I can conclude. Thank you. My name is Anish Maiduri and I'm from Mechanical third year, fifth semester. And the subject is FEA, Finite Element Methods. Department of topic is gear to sliding velocity in wind turbine gearbox. Thank you.